Hi everyone. Today we'll discuss activity question week 11 and week 12. Okay. First of all, I'm audible to everyone.
Yes, sir.
Okay. So we'll have some good questions on those uh, activity questions. Some good questions on body clock. Okay, and also some good questions on two code also. We'll learn some concepts. Okay. So okay, I'll share my screen. My screen is visible, right? Hmm? Is my screen visible?
Yes, sir.
Okay. So yeah. Okay. So, so in front there are some theory questions. So in first two questions there in doubt. Okay. So the third question I asked about the third the third question I asked about uh, input impedance. Okay. So for calculating input impedance, so can you tell me that what is the diagram of two port? What is the basic diagram of two port? Hello. Hello. Am I audible? Hello.
Yes, sir.
Okay. Please response, guys. Okay. Okay, so tell me what is the basic block diagram of a two port? What will be if it is a two port, then this will be plus minus V1. This will be plus minus V2. What will be the current directions? It will be inside the network or outside the network. Like it will be inward or outward. Hello, hello. Am I audible, guys? Guys, if you are not interested, then I will not discuss. Okay, you have to join with me. I will discuss only when like you guys need it. If you don't have any art for learning it, then directly tell me. I will stop the session, and I will also, like, I already provided the solution itself. In the PDF itself there are solutions. So if you don't want any discussion, then tell me, like, directly. Like, it's not, the thing is, it will save your time also, it's save my time also. Is there any need of discussion or what? If it is there, then tell me, and if it is not there, then also tell me. I will stop the session here. So should I stop the session? Hello, guys, you can be frank. Okay, like, it's not a formal meeting. Okay, I'm just discussing because I thought that, like, solving these questions will be like much more helpful for learning your subject. That's why. Okay, so Is if it is there is no doubt, then you can leave the, you can all can say me, and you can also leave the meeting. Is there any doubt in these two activity week questions? If anyone have any doubt, then directly tell me. First of all, am I audible?
Yes, sir.
So is there any need of discussion? Which one? Which one should I discuss? If I want to solve, if you want me to solve every question from basic, then you have to join. You also have to participate. I will not solve by only like, okay, okay. What about others? Okay. So this is a two-port network, basic two-port. So this is my V in, this is my I in, this is my V2, this is my I2. Okay. So uh, Z in will be whatever the input voltage I am applying divided by whatever the input, whatever the current is going. So see, for a particular circuit, it is a general rule that if you want to calculate the impedance from looking from that node, okay, let's say there is a network, there is something, a network is there, okay, and there is something up, like somewhere there is a port, okay, here there is somewhere a port is there, okay, and if you want to measure the looking in impedance from here, you want to measure the looking in impedance from this node, okay, look, and so obviously if you want to measure the impedance, you need at least 2 points. You can measure the impedance between 2 points. So it is like the saying this, that we want to measure input impedance from this node is useless unless we have a reference node. So when I am telling that when someone tells that that we are measuring our input impedance from this node, it is already assumed that we are assuming the second node as a ground node or the reference node. Okay, so this is pre-assumed, and then we solve the question. But here the thing is, here both the ports for input and output are given. Okay, so for generic rule is, if you want to calculate the impedance, you have to apply a test voltage there. If you apply a test voltage there, okay, and you have to measure the current. Okay, this is Vt and this is It. You have to measure the current which is flowing from the test voltage you applied, and you divide the test voltage by the test current. Okay, what you have measured, that will give you the input impedance looking from this node. Okay, so the thing is, for this two port, our input impedance is given, our input voltage is given V1, and also our input current is also given I1. So if I want to find the Z in means what is the input I'm giving.
Z in will be V1 by I in.
Yeah, that will be
Or
V.
looking
Exactly.
at the node from that positive terminal.
Yeah, that will be V1 by I. So V1 is given, that is 10 volt. I1 is also given, that is 2 ampere. That will be 5 ohm. Okay.
Yeah, yeah.
Yeah. So generally, I can tell you that. So that is not actually in your syllabus. Okay. So this is the input impedance. Okay. Generally, this input impedance is what? This input impedance is Z11. Z11. But there is a constant. So okay, let me tell you the first what is Z matrix first. Then I will tell you this what is Z11. Okay, and there is
Yes, sir.
Z22. Okay, the thing is, so the this Z in is not related to Z11. Okay, it's a generic. Okay, whatever I told you till now, it's for a particular node. You have to apply a test voltage. You have to measure the test current. That will give you the input impedance looking from that node. That node may be in the input, maybe in the output, maybe somewhere in the middle, whatever. Okay, that is a generic rule. But the thing is, for describe a particular network, we can use a different kind of matrix. Okay, so there are different kind of parameters are there. Okay, so some such parameters are z parameters. Okay, admittance impedance parameters, admittance parameter, hybrid parameters, transmission parameters. Okay, so abcd parameters, there are multiple kind of parameters are there. Among them the most useful networks are, sorry, parameters are z parameters and y parameters. Okay, these are the most useful parameters. Okay, and these parameters, these z parameters, obviously z means what? Z means obviously all will be impedances. Okay, all will be impedance. Okay, and y means 1 by z. Okay, that all will be admittances. Okay, so this is the like so these matrix. So generally these parameters will be in the form of matrix. Okay, so these matrix, if you have this matrix, you can like describe the system within a glance. That's why we make these systems. Whatever these actually matrices give the coefficients of the relation between the input current and the output voltage and the input current, these kind of things. Okay, I will describe you everything. Okay, but this is the first brief that you have to remember. Okay.
Sir,
Mhm.
sir, if we find that Z impedance, then 1 by Z will be Y.
Uh,
So,
so
is it so?
no, no,
So, is it so that we don't have to calculate that Y separately?
no, that is not a thing. If you have a some particular some z, okay, that will not directly give you the impedance matrix. That is a that is the thing is like if you have the
Generalized.
yeah, that is the thing is if you have a particular node point, and if you have the impedance, if you invert the impedance, then will give you the that will give you the that will give you the admittance at that point. Okay, let me finish first, then your all these doubts will be clear. Okay, don't worry. Okay, but the thing is the generic rule is if you have the z matrix, you can find the y matrix, but it is not directly inverting every element. Okay, it is not directly that if you have a 1 ohm, okay, and a particular in a matrix, if you, sorry, 2 ohm, and it is not, the thing is the admittance will be 1 by 2. Okay, you should take some precautions there. Okay, I will tell you, don't worry.
Okay,
So
sir.
okay, so the thing is uh, in this particular network, okay, in this particular network, this is v1, this is v2, and see here, both these ports are now open circuited, right? Both these ports are now open circuited. Now,
Yes, sir.
now this, if I write the relation between these four parameters we have, right? I1, this is I1, this is I in I1, I1, I2, V1, and V2. Okay, so V1 will be I1 into Z11 plus I2 into Z12. Okay, this V2 will be I1 into Z21 plus I2 into Z22. Okay, so generally, if if these output ports and input ports are open circuited, generally this Z11 term and Z22 term are the respectively input impedances and the output impedances. But the thing is, a constant here is these ports should be open circuited, but that is not the thing, right? Okay, so the thing is, and also the thing this Z12 and the Z21 are the trans impedance of from input side to output side, or from output side to input side. Okay, trans impedance means it's nothing but the like whatever the cause of the output port in our input port. It's like that. Okay, the effect of the output port in the, I told you also in the MOSFET part also. Okay, this is the thing. This is denoting this is the effect of output port, input port, and input port to output port. Nothing like not fancy, like uh, not much more complicated these things. Okay, this is the, these describe the relation between the V1 and I2. So like someone can say that, sir, we are giving the V1 in the input side, we should only get the I1 and we should get the relation between only I1 and V1. But that is not the case. The output current also have some effect on the input voltage. Okay, so these Z11 constant term or the parameter will describe that portion. Okay, and similarly for the output, Z21 will be describe that portion. Okay, so if we write, is there a doubt?
No, sir. Okay, okay.
Okay. So if we write this in a matrix form, we can write it that V equal to, V means V1, V2 equal to Z11, Z22, sorry, Z212.
Z12, Z21, or Z22
Mhm.
into I1, I2,
Yeah.
I2.
So this is V equal to this Z matrix into I. Okay. So this is the impedance matrix. Okay. Now similarly we can say that I equal to Y matrix into V. Okay. This, what is this Y matrix? Admittance matrix. This is Y11, Y22, Y21. Sorry, Y. Sorry. Y12.
Y21, Y22.
Yeah. Okay. Now generally the relation between them. So there is a relation between them. Okay. Do you anyone know what is the relation between the impedance matrix and admittance matrix? So the relation between the impedance matrix and the admittance matrix are Z equals to Y inverse or Y equal to Z inverse, whatever. Y equal to Z inverse. Okay. But it doesn't mean that Y equal to 1 by Z. Okay. That is the point I was talking about in the beginning of the lecture. Let's say,
Yes, sir. It's matrices sort of visualization, but it is not equal to one by that thing.
exactly. So let's say we have a particular impedance matrix. Okay. Let's say we have 5, 2, 2, 2. Okay. So this is the Z
Yes.
matrix we have. Now what is
So,
the
sir,
impedance matrix? Admittance matrix.
sir, here we know that Z11 is 5, Z12 is 2,
Hmm.
Z21 is 2, and Z22 is 2.
Hmm.
So, why would be like Y11, Y12, Y21, Y22? Let's find that Y11
Hmm.
and Y2
Hmm.
thing. So, how can we do that?
So we have to do the Z inverse here. We all know how to do matrix inverse. Okay, for a 2 cross 2, it's a very easy formula also. Okay, so for 2 cross 2 matrix, what do we have to do for to invert the Z matrix? So how can we get? We can get the Y matrix from inverting this Z matrix. How can we get the Y matrix? Now, tell me, how can I do? It's a simple math calculation. How to invert a 2 cross 2 matrix? So we have to take the adjoint matrix and we have to divide it by the determinant, right?
Yes, sir. Yeah.
Yeah. So what is the adjoint matrix here? It will be 2, 5, minus 2, minus 2. Okay. For the 2 cross 2 matrix, finding adjoint matrix is very easy. We have to replace these two corner terms, main diagonal elements, principal diagonal elements, and off diagonal elements should be reversed in sign. Okay. So that's why we make this negative sign here. Okay. And we have to divide by how much? Determinant of this. So
Yes,
determinant
sir.
of this will
5
be,
into 2, like 5 into 2 minus 4.
yeah.
So 6.
So
6.
6. Yeah. So our Y matrix will be how much?
So our Y
1
matrix
by
will
3
be,
minus 1 by 3 minus 1 by
yes,
3 my 5 by
and 5
6.
by
Yeah.
5 by 6.
So that's why. But if you see now, if someone do that like that, if someone from this, if someone say that Y equal to 1 by 5, 1 by 2, 1 by 2, 1 by 2, that will be completely wrong, right?
Yes, sir.
Yeah, so we can't directly invert the elements. We have to find the admittances. We have to see as a matrix format. I think this part is clear, right?
Yes, sir. Clear.
Yeah. So now I will say you some properties. Okay. See, if a particular circuit is symmetrical, there is two particular properties of what to say, of a circuit. Special cases. If a circuit is symmetrical, okay, I will say what is symmetricity, what is reciprocity. Okay. Okay. This is parameter. For Z parameter, if a particular circuit, okay, is symmetrical, okay, then Z12 should, sorry, Z11 should be Z22. Okay. And if it is reciprocal, then it will be Z21 equal to Z12. Okay. For Y parameter, it is same. Y11 equal to Y22, Y21 equal to Y12. Okay. So these two parameters you also need. There are also T parameters are there. There are also H parameters are there. For T parameters, the symmetric condition will be A equal to D. Okay, not don't go like this part. Okay, you don't need this. Okay, these two are more than enough for you. Okay, so there will be, here it will be
Yes, sir.
Y11 equal to
Y11 is equals to Y22 and Y21 is equals to Y12.
Y12. Now the thing is, what is mean by reciprocal or symmetrical? Okay.
Sir, what I can imagine, a symmetrical form would be like if we are sitting on a one point, if we take a look on the right side, it should be same as equal to the left side look. Like both are identical.
Yeah, yeah.
So
That's
it, it is
that's
like
yeah,
symmetricity, and then reciprocal is like one part is there, and then second part is it's reciprocal. Like if it is in the positive y-axis, then the second part would be in negative y-axis.
you can't. How can you
No, no,
imagine
sir,
the?
no. No, I just multiplied that to minus. No, that not way. Like reciprocal. Like
Okay, okay. I will tell you. Your approach is right. Okay. See, let's say we have a circuit. We have a network here. Okay, and we are dividing this network. If we can divide this network into two equal half parts, like this one. Let's say we are dividing this network. Let's say we network have a particular resistor here, okay, inductor here, a capacitor here, okay, and another inductor here. Okay, now we are dividing into two equal parts. Now this will be connected, and let's say this exactly mirror image of this one. See here, if we place a mirror in the middle, we place a mirror, that will be exactly the mirror image of the first one. Then that circuit is called as a symmetrical circuit. Like what? This inductor will be placed here. This inductor will be placed here. This resistance will be placed here. Okay. This inductor will be placed here. This capacitance will be placed here. This is the exact symmetrical. So from a mid of the circuit, if we place a particular mirror, that will be exactly the mirror image of the second half. Then that circuit called as a symmetrical circuit. Okay, I will give you the examples also. Don't worry, you will feel it. Okay, and what is the reciprocal circuit? Reciprocal circuit, if you looking from this side and if you looking from this side, both these from looking from that both that side will be exactly similar, equivalent. Then that circuit is called as reciprocal. Okay, now I can give you both. If a circuit can have, is there a doubt?
No, sir, no doubt.
So a circuit can have both symmetrical and what to say, reciprocal. Let's say I am assuming a resistor here and a resistor here, a resistor here, a resistor here, and a resistor here. Let's say we are giving this, say 5, 2, 5, 3, 3. This circuit is both reciprocal and symmetrical.
Yes, sir.
Yeah, because see, from this side if you see and from this side if you see, this circuit is exactly similar. Okay, and if you like, if
From this common node, that 3
yeah,
point
so
junction.
if I reform it like this, this circuit can be reformed by this side, right, circuit, right? Because see, here is a 2 ohm resistor. Now I have divided into two parallel of 4 ohm. That will be equivalent 2 ohm, right?
Yes, sir.
So if you divide it from this side, this particular point, see, this network is
Symmetrical axis.
this network is exactly mirror image of this network.
Yeah, yeah.
Yeah, so that's why this network is all symmetrical as well as reciprocal. Okay.
Yes, sir.
Yeah, so I think this point is clear to you guys. Okay, now with this base I will try to solve the questions. Okay, now obviously z in will be 10 by 2, that will be
5 ohms.
5 ohms. Okay, now what will be the this one, what will be this one? Similar, right? Similar, exactly similar. If what you have for finding the admittance for a particular node, you have to give a test voltage, you have to measure the test current, and you have to divide by divide that voltage, divide by the current by the voltage. That will give you the admittance. That will give the y11. Okay. Similarly,
Okay, so 0.2.
obviously 0. So 1 2 by 10. Okay, that will be 0.2. Okay.
Yeah,
So I
current
think,
by voltage.
yeah, current by voltage. For finding the admittance, you have to divide. You have to do current by voltage. For impedance, voltage by current. Simple. Okay.
Okay, okay.
So this is a theory question. Okay. Network only resistor, inductor, and capacitor. Admittance parameter will be what? Linear. A particular circuit with only resistor, capacitor, and inductor. These are passive elements. Okay. These elements cannot cause non-linearity. This lumped element cannot cause non-linearity. That's why non-linearity
Yes,
came
sir.
on.
There
No,
is no diode like
yeah, yeah,
non-linear element. Only linear elements are there, passive
yeah,
elements. So it
yeah.
will be
Only,
linear.
yeah, these all are passive elements. That's why they can't cause non-linearity. Non-linearity can be caused by op amps, diodes, or maybe MOSFETs, this kind of things. Okay, active elements should be there to cause non-linearity. Okay, so this will be linear. Okay, so uh, this is a simple basic theory questions I have asked also.
Impedance, Z parameters are impedance.
Mm-hmm. This I already discussed. Okay, this will be this. Okay.
Yes, sir. And sixth, yes.
Now solve the eighth question. How now? Tell me how to solve the eighth question.
So, sir, in a matrix, we know two parameters of impedance Z11 and Z12.
Okay.
So, two things we know, that 10 ohm and then 5 ohm.
Mhm. I'm
So, we have,
removing these parts. Okay. If you want to, like, do you want to take a screenshot or what? Like, I will then wait for a bit. Okay. If you want to take a screenshot, you can take a screenshot. I'm removing this part. Okay. So yeah. So what do we know? We know V1 equal to Z11 I1 plus Z12 I2. These all parameters are given. These all
Yes,
parameters are
sir.
given. Only you have to calculate. Okay. So you can easily calculate. So Z11 into 2, 10 into 2 means 20. 20 plus 5 is 25. Option D will be right answer. Okay. Now solve the this ninth one. How can I solve the ninth one? How can you solve the ninth one? If we calculate the V1 and I1, if we calculate the V2 and I2, okay, so the total power will be V1 I1 plus V2 I2, right? V1 I1 plus V2 I2, right? This will be the our total power. Now see, I1 also given, I2 also given, V1 also given, V2 also given. You just have to multiply. You may like you may have solved this all question. Okay, and just I'm briefing it. Okay. Now what is the yeah? See this relationship I already told you. Okay.
Sir, D. Y is Z inverse.
Actually, these both are right.
Yeah,
These both are right. Okay.
both are inverse of each other. So
Yeah, yeah,
anyway, we can write.
yeah, yeah. So these are simple questions are there. Okay. A star network with these all three resistance, all the whatever the equivalent delta from converting star to delta. What is the see? Do you know what is the like if you convert from star to delta or delta to star? What is the resistance changes? How to calculate? Do you know
Sir,
what? Just tell me what is the procedure. Yeah, three is the right answer. Tell me the procedure. What is the formula to convert? If there is a star network like this, okay, let's say this is R1, this is R2, this is R3. We are converting it to delta. Okay, let's say this is RA, this is RB, this is RC. So what will be RB? RA first.
Sir, I remember that way that R12 will be R1 R2 plus R2 R3 plus R3 R1 divided by R3. That we got R12, and similarly
Yeah. That is
R2
that,
3 R3 1. So both three will be 1 ohms.
yeah,
So
both
net,
will be on ohms.
uh,
Okay, these
net
remembering these formulas are different for like different for everyone. I remember like this. I for I see that these two nodes from between these two nodes I have to calculate the resistances. So I saw whatever the what is the resistance connected to this node. This is R1 and R3, right? So I remember like this R1 plus R3 plus these two multiplication R1 R3 by of like what is not touched, that is R1 R3 by R2. Okay, everyone like remembering these formulas like for different will be different for everyone. Okay, so everyone is right. Same someone like does a different thing. Okay, that will also fine. Okay, so this will be the thing. Okay, that will so if you put the formulas all will be one. Okay, so one will be that will be every resistance will be three. See some generic formulas I can tell you. Okay, see if you are trying to convert a star to delta, delta to star, always you can
sir,
notice that
sir,
what.
can you tell me your approach to like solve this question?
Yeah, so I'm telling you. Okay, if you want to solve this directly, okay, so see if you so this is some genetic rule. Okay, if you convert star to delta, generally z increase impedance increases. Okay, and the special case is if all the three resistance are same, then the delta resistance will be three times. 3 into like whatever be the Z. Okay, Z here. Each limb will be have
Okay.
convert. Each limb will be have some Z. Okay, it will be 3 times. Okay, and opposite for the delta to star. If you go from delta to star, okay, the impedance decreases.
Divided by 3.
Yeah, but the thing is, I am saying impedance decreases. Okay, remember for inductor and capacitor, for resistance and inductor, it will be same, but for the capacitor it will be different. Okay, you think in the next session you will tell me that what will be that difference. Okay, you have to be careful about the like values. Okay, in capacitor you should be careful. Inductor and capacitor will directly tell. Okay. So the thing is, for capacitor, for L and R, okay, it will be L by 3L and 3R. But for the capacitor, it will be C by 3. Okay, it will be C by 3. Similarly, if it is 3L, sorry, not 3L. If it is here, if it is 3R, 3R. If it is L, it is R and C. It will be L by 3, R by 3. I am converting delta to star. Okay, R by 3 and 3C. Okay, you should be careful about this. Okay, capacitor, like many guys like they know the concepts, but while doing in the exam they fail to do it. Okay, they did this kind of silly mistakes and they lose the marks. Okay, now just a second. Okay, now tell me how to solve this 12th question. Is all things are given. I gave this network intentionally because I want to like deliver some concepts here. Okay, how to form for a part. If some network is given, how to form the Z impedance matrix and the Y impedance matrices without solving the like rigorous that kind of equation analysis. So for this you have to find uh, like you have to find the matrix, Z matrix, right? Okay, I asked what is Z 2 1. So finally you have to find the Z matrix here. So see, remember this thing. Okay, I will tell you something. Okay, you can see that like if you practice more questions, this kind of concepts you will get. Okay, so there are mainly two kind of networks we will face in the industry. Okay, these things are the star, these T networks, and the pi networks. Okay, let's say this is R1, R2, R3. This is R1, R2, R3. So always remember, finding the Z impedance for a particular T matrix is very much easier. Similarly, for a particular pi circuit, finding Y matrix, admittance matrix will be very much easier. Okay, so this is a T matrix given. So we can directly, if this is plus minus V1 and this is I1, if this is plus minus V1, this is I1, sorry, V2, I2. Okay, then our Z matrix will directly be R1 plus R3. Okay, in this loop, whatever be the resistance is coming, R1, R3. For Z22, this loop, whatever be the resistance are coming, R2
R2 plus
plus
R3.
R3, and the mid one will be this one only, R3. Now, can you say me, is this circuit is reciprocal or the symmetrical?
Sir, like it is reciprocal because R3 is same.
Exactly, this is a reciprocal circuit.
but not symmetrical because Z11 is not equal to Z22. Am I right?
Yeah. Like with seeing this, without giving the value, we can't say that this is a reciprocal or this is the symmetrical or not. But this for sure this is a symmetrical network because these are equal. Okay.
Sir, reciprocal.
Sorry, reciprocal. Yeah,
Reciprocal.
reciprocal. This will be reciprocal. Okay. Now see, for this Y matrix, it will be finding Y matrix will be very much easier for the pi circuit. Okay. Now, if someone says that for a T network, you find the find the impedance matrix, admittance matrix. What you will do? You will find the Z matrix, then you will directly invert it. It will be much more easier, much more convenient for you. Okay. Similarly, for the pi network, if someone tells you to find the Z matrix, you will find the Y matrix and you will directly inverse it. Bas. Only you have to do these things. Okay. So for this, if this is R1, this is the impedance is given. We have to convert this for first admittances. So R1 will give you Y1. Y1 means 1 by R1. Okay. Y1. This is not Y11. This is Y1. Okay. So this is 1 by this is Y. This will give you Y2.
1 by R2.
Y3. This is Y2 will be 1 by R2. This will be 1 by R3. But simple. Okay. So this will be what this will be? This will be Y1 plus Y2. This will be Y2 plus Y3. This will be minus of Y1. This will be minus of Y2. This will be minus of Y2. Okay. So you have to convert. You have to care about this minus. Okay. Okay. You got. If you
Sir, we have to like remember this representation. Y1 plus Y2 minus.
If you remember this representation, that will be very much convenient for solving the questions. You can also derive that. Okay, if you write the equation, you can also derive that. See, if I am deriving it in front of you also. So this is I1. Okay, I1 is going. This I2 is coming. So whatever be the what is coming here, I1 plus I2, right?
Yeah, correct.
So V1 will be I1 R1 plus I1 plus I2. Sorry, I1 plus
I2 into R3.
R3. So I1 into R1 plus R3 plus R3 I2, right? See, this is Z11, this is Z12. See.
Yeah, correct.
So similarly, you can derive also. But if you remember this, okay, so if you in the exam, you don't have to derive it and you will directly move forward with the question. That's why I'm telling you, if you remember, and also remembering this is not a difficult job also. Okay, and you don't have to remember also. If you practice enough number of questions, it will automatically go into your brain. Okay.
Okay, sir.
Okay. So what will be this for this circuit? What will be? So will not solve any will not do any handwritten solution. Will directly with our intention. So what is RA here? RA is 5. See, RB is 5 and RC is 7. RB is 5. Can you say me that with this only with if you don't know any of this, if you don't know any of this, I'm reviewing all of this. Okay. How can I delete it? Yeah. So this is 5. This is 5. This is 7. Okay. Now tell me that this is 7. Tell me that it is a reciprocal, it's a symmetrical, or both.
Sir, it is both.
Why it is both?
Because sir, if we look at
because see if this network I can reform into like this.
And from looking at the left side and right side, exactly same. So it is reciprocal also.
Can I reform like this or what? Is there any doubt in this reformation?
No, sir. Now put on the axis, middle
Now,
axis.
if I put an axis in the middle, looking from looking from this side and looking from this side will be exactly mirror image of each other. So that's why this will give me symmetrical. Okay. Now if you look from this side and if you look from this side, both these looking will be exactly equal. That's why these are also reciprocal. Okay.
Yeah.
So like, can you tell me what is the profit of being a reciprocal circuit, having a reciprocal circuit? Like why we're actually
That
bothering about this?
Z1,
Mhm.
Z12 and Z21 will be.
Yeah, that is a theoretical answer. Like, what is the, like, in the physical level, what is
Like, sir, half
what,
circuit will behave the same as the other half circuit.
okay, then so what? Hello?
Yes, sir, we don't know.
Yeah. The thing is, uh, if a particular circuit is a reciprocal circuit, now you can interchange the load and the input. So for that, if you interchange, now your analysis will be much more easier. Okay. And someone told that, yeah, obviously half circuit will be behave exactly equal to the other half circuit. So we have to analyze only half. Okay, other half will be predictable for us. We don't have to go through the rigorous analysis of other half. So analysis of a circuit will be much more easier. Okay, and
Yeah.
and this is a like out of the box thing. The thing is, if a particular reciprocal circuit is there, and uh, if differential signals are applied, okay, so then you will get a lot of benefits. Okay, differential signal means if you increasing this with a particular voltage, let's say delta V amount, you are decreasing also this voltage by a delta V amount. Okay, this is called as differential signals. We are increasing one side, we are decreasing another side. Okay, then these nodes will be zero. These middle nodes will be zero. Okay, so I will not go about that, because if that will be zero, these whole resistance we can omit. Okay, that is the another thing that is called as half circuit problems. Okay, but we will not go at that side, but that is also a thing. Okay, you must know that like if we have a particular reciprocal circuit, then we get this kind of advantages to analyze the circuits. Okay, for now this is clear, right?
Yes, sir.
Yeah. So obviously, what is be Z12? Z12 will be how much? 7,
7.
because Z12 will term only the middle term. Okay. Is there any doubt in the 14th question? 14th question will be exactly similar as the 13th question. Just you have to find Y21. Can you directly find Y21? Like someone can do that. Someone can do for finding Y21. He will take Z21. He will directly he will do 1/3 and he will put the answer, and his answer will be wrong. So you have to careful about Y21. I told you in the beginning of the lecture, I told you how to calculate this Y matrix from the Z matrix. You will calculate and think you can do it. Okay. You just have to form this Z matrix. You have to invert it. Okay. You have to take the inverse of the Z matrix, and that Z matrix will give you Y21. Okay.
Yes, sir.
And do you know what is this Y21 in the BJT and the MOSFET? Okay. We read about the transconductance, this GM transconductance, right? Okay,
Yes, sir.
so that is this GM is this Y21 parameter. Okay,
Sir,
Y21
how?
is that is, you have to go through some analysis. Okay, that is the Y21 parameter. For now, it will be like if I go through that analysis, that will take some time. Okay, and also we will divert from our main point. Okay, but
Sir, can you tell
this
that
is
name again?
huh
That analysis name?
analysis name. Like
Yes.
if you particular for a particular MOS circuit, na, say a particular MOS circuit, if it is in the black box, okay, so it is like a two port, right? This is the input port, this is the output ports.
Yes, sir.
Okay, if you do analyze this, okay, this will give you this will give you y21 parameter as GM. If you equate this current equation of the MOSFET and we will do the this dependence of the voltage of the output voltage, this is VDS plus minus VDS, right? And this is plus minus VGS. Okay, that will give you the y21 as GM. Okay,
Okay, sir.
like in the if in another session, if there is more time is there, I will go through the whole derivation. I will tell you that why this is GM, why y21 parameters is GM. Okay, and this that thing is also simple. If you go to internet, if you type it, it will give you. Okay, it is a simple analysis only, but it is out of your scope. That's why I'm not telling. Okay, for the transformer V1, what is the relation? V1 by V2 equal to N1 by N2 equal to I2 by I1, right? So this is our right answer. Okay, obviously it's a 10 is to 1 is 10 is to 1. If the input voltage is 220, obviously the output voltage will be how much? 22. It will be divided by 10, right? Because
Yes, sir.
just now I told you V1 by V2 equal to N1 by N2. So
And two.
this is 220, and this is, I know, let's say is x. This is 10 by 1. So obviously x equal to
10x by
22.
x.
Okay, so okay, how can you solve the 17th question? Can you say me? How can you say the 17th question?
Uh, K is equals to M root L1 L2.
Okay, yes. K equal to m root. Uh, is it so? Okay. K equal to m root or m equal to k? Coupling factor. Okay. K equal. Yeah, mutual inductance. Yes, yes. This is a mutual. Okay. So we know we need what? We need the. Is it so? Mutual inductance equal to.
Sir, mutual inductance is equals to K times under root
Yeah,
L1
yeah, yeah,
L2.
yeah. That's why.
Yes,
Yeah,
sir.
that's why I'm getting confused. So mutual inductance equal to K into root over of L1 L2. Okay.
Just put in the values and we will get the
Yeah,
answer.
we'll obviously take that. 0.9 is there. It will be 10 into 5. So obviously it will be 45. Yeah.
In this question, only one like formula of that mutual
Yeah.
inductance is
Yeah,
used.
this is the mutual inductance formula. I got confused that like she told that, yeah, so that's why. Okay. So
Yes,
this
sir.
will
That's
be.
why.
Mhm. So okay, so this thing is also very simple thing. Okay, a transformer has a trans ratio of this one, and a 4 ohm resistor is connected as secondary winding. Okay, so what will be the equivalent resistance seen from the primary? Can you like know what is the formula to convert to refer from input side to output side or output side to input side?
R, R equivalent is equals to R into N1 upon N2.
Exactly. No. R into N into square N1 by N2 square. If you're looking from the input side, okay, there will be R out into N1 by N2 square. Okay, and if you look from the output side, it will be R in into N2 by N1 square. Okay, so here R out is 4 and this is 2 square, so it will be 16. Okay,
Yes, sir.
because like voltage and current both will be there for converting. That's why. Okay,
Sir, can you please like draw the diagram of this 18th question and
18th question. Okay,
yes, sir, like then
okay, okay.
explain.
So this is 2:1 is given. Here at output there is a resistance is given R equal to 4 ohm. Okay, and we have to tell what is the input impedance looking from here. Looking from here,
Okay,
right?
okay.
Now the thing is, it is a generic formula. Whatever be the like what while you are starting from there. Okay, so this will be your source. This will be your destination. Okay, I remember like this: source into destination by source into so source into sorry resistance into destination by source square. Okay, so this is my destination, right? And this is my source. So destination is 2, this is 1. That's why I remember like this. You will not get confused with this. Okay, you will not have to remember what is the input, what is the output. You need to only see what is the destination of mine, what is the source of mine. Okay, this is my starting point, this is my destination. Okay, so our resistance will be resistance into destination by source square. Okay, so if you look from here, if let's say if there is a resistance there, I am looking from here, let's say this is Rx. Okay,
They will
and
be
if
exactly opposite, the destination and source,
yeah, destination and source will be exactly opposite.
because we are looking from that secondary side.
Yeah. So yeah, this is a simple question. Last one. Okay. So we are moving forward. Activity
To
question 8.
minimize energy loss and maximize power transfer.
Yeah. These kind of theory questions I put for like boosting the concepts. Okay. So this is an interesting activity questions. I found some good questions also here. Okay. How many have tried this question? This question. 15th question. How many have you tried?
No, sir, not tried. I have not tried.
Okay, anyone tried this
I
one?
have also tried.
You tried?
No.
I'm not getting, like, your voice is so drowsy. Like,
No, sir. No,
okay,
sir.
no. Okay. So okay, before 15th one, is there any doubt? Okay, because 15th one is a very good question. Okay, and also there are some questions in the previous. Uh, there should be some diagram questions. Okay, maybe in the next week also they are. I also put some diagram questions. Okay, we'll discuss this. Okay. Okay, tell me, is like how many of you dies before 15th one? Because if you solve the 15th question, your body plot uh, concept will be completely clear. Okay, that one question will come like wholly revise your full body plot.
Sir, you can just brief out the like explanation on body blood, and then we can proceed with the question.
Okay, for the first question, the thing is, we in the control system, we obviously always assume zero initial condition and then derive the transfer function. So deriving the transfer function also assumes that we are assuming the initial conditions is zero. Okay, initial conditions are zero means, do you know what is the physical meaning of initial conditions having zero? Anyone know this? What do you mean by physical like no initial conditions? Hello.
No, sir.
The physical meaning of no initial condition is all the lumped element are completely discharged. That means if a capacitor having initial voltage that is already discharged, we assumed there is no initial voltage across the capacitor and there is no initial charges across in a particular inductor. And also a resistor cannot like store any kind of like these energy forms. Okay, that's why resistance we are not bothering about. For the inductors and capacitors, these are the storing elements. So we are assuming that the energy at the starting of the analysis are zero. Energy stored in these elements are zero. Okay, so that is the physical meaning of the zero initial condition. Okay, so obviously this is done. Okay, And obviously this is a particular differential equation. Okay, for derivative parameter you will for derivation you will put s. Okay, for double derivative you will put s square. So obviously s square y of s plus 3s y of s. This is a property of Laplace transform. Okay, you know now property of Laplace transforms.
Yes, sir.
Okay.
Yes, sir. Yeah.
Yeah. Actually, if the derivative property, if derivative is there, okay, I will in the upcoming questions. Maybe I will tell if there is a question. Okay, so this will be plus 2y of s equal to x of s. So obviously, y of s by x of s will be my transfer function. Will be 1 by s square plus 3s plus 2. So yeah, this one will be right answer. So yeah, so this one is also a simple question. What will you do in a time domain? What happens? See, if a particular system is there, okay, let's say this is h of t, and if we applying some x of t signal, so y of t will be how much? Do you know what is y of t then? Y of t will be x of
Output
t,
C
x of t.
x of t into
into h of t.
No, not x of t into x of t convoluted with h of t. Okay, h of t is the impulse response of a particular system. Okay, but for the this convolution operation you have to perform, but for the that's why the thing, that's why you are moving. Let's see, before learning the Laplace transform we are always analyze a particular system using our time domain approach. Whatever we learned in time domain, we always apply those concepts and we solve the questions. But then why do we need to like know what is Laplace transform and this Fourier transform, this kind of transform things, frequency domain, time domain, this kind of messy things? Why we need to learn? The thing is, for a particular network, these particular tools are there in the mathematics. Like these particular tools are derived, are used for like analyzing a particular complex network. Okay, it is not convenient to analyze always in the time domain, because in time domain there, if there is non-linearity, then we will be finished. We can't intuitively say intuitively in, leave intuitively, you can't say about the full analysis also. Okay, but the thing is, if you have some tools that will simplify your particular circuit, then it will be much more easier for analyzing a circuit. So that tool is your Laplace transform. So Laplace transform actually helps us to convert the time domain network to a frequency domain network. In frequency domain network, you don't have to perform this kind of convolution operation. You just directly, what you will do, you will directly take x of t and you transform it to x of s. Okay, this will transform to h of s, and
Y
now
of S.
y of s will be directly x of s into h of s. Simply this. You have to just multiply these things. Okay. But for doing the convolution, you have to take one signal at positive direction. You have to take opposite signal in the anti-positive, like negative direction. Then you have to pass this signal. You have to shift by one unit of time, and you have to multiply. Then you have to add. Okay. So for this, do you know how to do convolution? Do you guys know?
No, sir.
sir
Okay.
integral
Then
things, right, sir?
yeah, it's an integral. It's an integral. Okay, I'll not go about that way. Okay, so you have to do so just know that you have to do convolution operation in time domain. To avoid this kind of complexities, we are using this frequency domain. Okay, that will be much more easier for us for analyzing a circuit. Okay, so obviously this will be just multiplication of y of s will be multiplication of this h of s and this of s is the multiplication problem. So I think B will be the answer. Okay. So obviously there is the system transfer function is this one. What will be the order? Order will be 2. Order is the highest degree in the denominator. Okay, that will be the order of the system. And I will tell you one thing. Okay, that thing is non-linear also. Leave it. That will be much a little bit advanced.
Sir, I have one small doubt.
Yeah.
Sir, in this fourth question, we are dividing a linear function by a quadratic function.
Mm-hmm.
Okay. So linear by quadratic will like end up into 1 by linear. So order would be like 1.
No, that is not the thing. The order will be order is like the order is the thing. How many poles a particular system have? See. These poles, zeros. This will be these are imaginary concepts. Okay. The thing is, order is defined by the how many independent voltages. How many uh, independent voltages are assigned to the storing element in a particular circuit. Let's say we have a circuit. Okay. This C. Let's say having L. Okay. Let's say this C. This kind of circuit is there. So for this for describing the circuit, we have to assign a voltage here and also have to assign a voltage here. These are the independent voltages. Okay. So these independent voltages will decide what is the order of the circuit. Okay, ultimately these are the physical, this is the physical thing. And if you don't go to this one, you just have to do the pole zero diagram of this one. Okay, this will have two poles in the left of S plane. The poles location will be how much? It will be so -4 plus minus root over 16 minus 4. Yeah, this will be something here. The poles will be, if this is S
Okay,
plane,
but
this
0
sigma.
I know that. Yes.
Okay, you guys don't know about this.
No sir, no.
We know.
We know that.
You guys know now what is pole, what is zeros.
Yes, sir, exactly. We know.
Yeah.
Yes sir.
So order will be dependent. Order is decided by how many poles are there. Our poles is also coming from the how many independent voltages are there. Okay. So the thing is the order will be decided by how many poles in a particular circuit. What is the pole? How many poles will be there in a particular circuit? This is two. That's why you're giving this two. And ultimately the thing is what is the highest order that will give the number of poles. Okay, that's why I told you that what is the highest order. This is the number of poles.
And sir,
But
0 would be -1.
yeah, that zero will be -1.
Yeah, that from that y axis.
And
Uh,
do you know about the concept of damping also?
Yes, sir.
Then
It is critically damped, over damped, under damped.
Not in this case, but I do know in spring case.
Okay, okay. I will not go about this. Okay, but this is a under damped system. Okay, we'll leave it. Uh,
So can you give a little bit explanation about it?
if I want, if I want to give now, I have to derive something. Okay, other than that, other than it is like it will be like will not understand anything. I have to give some derivation also. After that, I have to come from a particular base, right? So if that base is not clear, that will be like be a bit hard for understanding you guys. Okay, the thing is for damping you have to find zeta. Okay, zeta is the damping factor. Okay, so that zeta will tell you what damping is present in a particular circuit. I will tell you what will be the response if a particular say let's say we are giving a input voltage of 1 volt. Let's say we are giving an input voltage of 1 volt. Okay, this is our input voltage. And okay, I will tell you briefly. Okay. The thing is, if I talk about this and you guys also have some interest, okay, you will not learn anything. Okay, see, I am taking a particular simple RC circuit. Okay,
Okay, sir.
I'm not doing it in a block diagram level because if I do it in a block diagram level, okay, you will not feel it. If I go into the element level, then only you can feel it. Okay, that's why I'm doing in a element level. Block diagram, in a block diagram level, it will be much more easier for me. But the thing is, you will not get anything. Let's say if this is R, this is C, and we are applying a voltage V. This is, let's say this is something V volt. Okay, and we want this output voltage. First of all, what is this circuit? What is the name of the circuit?
it is a simple RC circuit.
A simple answer is like why I derive this, like why I use this in a particular. I am taking this circuit because this is used in some places, right? This has some application. I'm asking about what is the application of the circuit.
Yes, sir. Low pass filter and high pass filter, like
What
It's
is
low
this?
pass.
rearranging.
This is low pass. Okay, this is a low pass filter. What low pass filter does? Low pass filter removes the high frequency elements. Okay, what are the high frequency elements? High frequency elements are the harmonics in a particular source. That's why you need a low pass filter. A low pass filter basically removes the harmonics from a particular source. So what is the harmonics? Let's say we have a particular sinusoidal, but we will not get this pure sinusoidal. This sinusoidal have some harmonics. Okay, this has some harmonics. This is the third order harmonics, fifth order harmonics are there, the seventh order harmonics are there. Okay, so these harmonics will be present. That's why after this harmonic, my sinusoidal wave will be this kind of distorted. Will not get pure sinusoid. So to remove these harmonics, we need a low pass filter. Okay, so that's why you use a low pass filter. So now the thing is, what will be the output voltage? My output voltage will not. So this is my input voltage V. My output voltage will follow the V voltage, but after some time it will catch the output voltage. After some time, this will be like this, right? This will be
Yes,
like
sir.
this. Now,
Yeah.
this is a simple RC charging I have drawn. Okay. Now see, this circuit is following this way. I told you, and you told me, you agreed with me. But it need not to be following only this way, right? It can it can do this way also. Okay, it can follow this way also. And let's suppose this circuit is very slow, then it will go like this. Okay. Okay.
Yes, sir.
Now, and also there is a case. There is a case also. It will follow this way also, right? But it's all these diagrams will be true only if this circuit is stable. Now this circuit is a stable circuit. I have taken a stable circuit. Okay, for unstable circuit it may not follow. It will not follow. For unstable circuit it will not follow, first of all. Okay, so I'll not go about the unstable circuits. I assume this is a stable circuit. Okay, and this will follow. Now see,
Sir, can you give that quick graph of that unstable circuit? How
unstable.
it would be
The
like?
thing is, we can't predict that. That is the main thing. That's why you are not making an unstable circuit. For an unstable circuit, we can't predict what is the graph of the an unstable circuit. That can do this way, something, whatever. Okay, we can't predict the nature of a particular unstable circuit.
Okay.
So I am like drawing this again. So let's say this is my response. This is my response. This is my response. Okay, and this is my response.
And sir, when would the condition of unstable will happen?
When the poles will be when the poles of a particular circuit will be right hand side of a S plane. Okay, right hand side of a S plane, or multiple poles in j omega axis. Okay, or multiple poles in zero. I'll not go in that part. Okay, that will be out of your scope. Okay. See, now this is also not there in your syllabus. Okay, I'm giving you because this will give you a brief feel about what is happening in the circuit. Okay, so this is my V out, this is my T. Now see, what is the optimum response? This is my optimum response. This will gives me the most fastest response. Okay, so that's why this is called as critically damped. These response are not overshooting, but these response are giving me the slow response. That's why this is called as overdamped. And this is the oscillatory. This behaves first as oscillatory, then it will settle at particular time. Okay, so this is called as underdamped. What does it physically means? Critically damped means the damping is exactly correct. Let's say you are hearing something in radio. You are adjusting the channel. at a particular frequency, you will get the maximum volume and the maximum clearance. Okay, that is the critically damped. Okay, that thing is also a particular frequency, that there is also a damping condition is there. That's why I'm taking this example. Okay, that is critically damped. But the thing is, you will get some like noisy thing. Okay, after some time you will get the clear. That is the under damped. That means that my whatever damping I have provided in the circuit, that is not exactly that is not optimum. Okay, and these things are these are over damped. That means it is my damping is bigger. Okay, that's why I'm not getting the first response. There is some lag in the system. Okay, that's why this is the over damped. You got the like. Are you getting? Are you following?
Yes, sir. We are.
Yes, sir.
Yeah. So that is the concept of damping. So for knowing this damping, we need to find one parameter, that is zeta. Okay, that is the damping parameter. I will not I will not go about the zeta parameter, but zeta tells us that what is the damping present in the circuit. So what you want in a practical case, what you want always a critically damped system, right?
Like
Because
Zeta have like ranges for that under damped.
there are many
critical
ranges. Correct. There are many ranges. There are many ranges of of zeta that will give you and for a critically damped there is no range. Critically damped there is no range. Critically damped is a particular pinpoint. Okay.
Yeah, sir.
Yeah. So this is all about the damping. Okay. Okay. Now this is a simple question. I will not talk about this. Okay. This is how can you solve this? This is also a simple question.
Sir, which question?
This one. Sixth one. I
Sixth
asked
one,
about.
we will convert that also all into that as domain.
Yeah. So if we this is
Then
R will be R,
find-
this will be SL, and this will be
Yes, sir.
1
And
by
one
SC.
by
Yes.
yes,
Yeah. So if you find that, you will get the answer. Okay. It is a simple
Yeah.
simple impedance network. This is RLC network. Okay. I think you can solve it.
A total impedance we can.
Yeah. Total impedance you have to do 1 by SC. I'm doing okay. I want 1 by SC plus R plus LS plus 1 by SC. That will be our V0 by V. Okay. So I'll ask only about the denominator after simplifying. Okay. This is also a very just you have to factorize. This is not it's a factorization problem. It will be what it will be 6 5 and 5 and 1, minus 5 and minus 1. This will be answer. No. 2 into 3. Okay.
Sir, -2 and -3. X
Yeah,
plus
-2 and
2,
-3.
S
Yeah.
plus 2 and S plus 3.
So you have to be careful about this. I also did the analysis.
Yes.
Okay. So del of t, it will be 1. Okay. The Laplace transform of del of t. This is also discussed in the classes also. Okay. Now, ninth question is a good question.
Yeah, that impulse signal.
Yeah.
Sir,
What is the
was
impulse
talking
response? First of all,
Impulse.
H of S is the impulse response, right? But this is S domain. 1 plus, so not 1 plus. This is S square plus 3S plus 2. For solving this question, Laplace transformation knowledge is important. Okay. So this is our H of S, right? Am I audible?
Yeah.
So this is our H of S. We need to find the time domain. This is the Laplace domain, right? We need to find the H of t. Okay.
Sir, we have to take the inverse Laplace transform.
Inverse Laplace transform. But the thing is, if you take the inverse Laplace transform of this signal, okay, you do the integration, okay, that will be time consuming. So what we will do, we will use the property of Laplace transform. Okay. So first to use the property of Laplace transform, you need to do the partial fraction of factorize partial fraction of this. So this will be 1 by S plus 2 into S plus 1. Yeah.
So that will be, we can write A by something
Exactly.
plus B
A
by
by S plus 2.
S into S plus
B by S plus 1.
S plus
yes,
1.
yes.
Okay. Now what I will do, we need to find the value of A and B, right? So you always, like you in the 11th and 12th in the mathematics also, you did the partial fraction like this. I will give you a short trick here. Okay. So what I generally do, okay, for calculating A value, I'm calculating A value. In this transformation, I omit this. I omit this and I put a is equal to -2 here. So what a will be? So if we put a is equal to
minus
-2,
one.
-1, a
Minus
equal
one.
to -1. Okay, and for
Yeah, for minus one, one हो गया sir. B is one.
b is 1. Everyone got it or not? If anyone doesn't got, I will explain it.
Yes, I got it.
Others got it now? If anyone have doubt, I will explain it in brief. I will in a very detailed manner. Okay, then if no one have doubt, I will move forward. Okay, so I got 1 by s plus 1 minus 1 by s plus 2, right? Right?
Yes
So
sir.
yeah, minus.
Yes sir, it is correct.
It will be minus, right? Because a was -1, b was b was 1. So a is this coefficient. What is the general form here? See, that's why I generally don't do step jumps. See, this was a by s plus 2 plus b by s plus 1, right? So our a is -1, b is 1, right? So what it will be? -1 by s plus 2 plus 1 by s plus 1. So it will be 1 by s plus 1 minus 1 by s plus 2. Got it?
Yes, sir.
Now what will be the inverse Laplace of this one?
E to the power minus t.
Minus t. What will be this one?
My
E to the power minus 2t.
Yeah. So e to the power of minus at ut has Laplace transform of 1 by s plus a. Okay. That's why I took the inverse Laplace. That's why we got this one. Okay. So what is our answer? This will be our answer. Okay.
Okay, okay sir.
Okay. So this kind of questions are there at C. This one I told you in before. It will be this one. Okay. Similarly for this one. What it will be? 1 by s plus 2 into minus 1 by s plus 3.
Plus 3.
Yeah. So you can directly do what is the what will be the answer. Okay.
Like, we can take the LCM of s
Yeah,
plus
yeah,
2s plus 3
yeah.
and
This
then
is
solve
simple
accordingly.
mathematical calculations are there. Okay.
S
These
plus
poles
3 minus.
-1 -3 will be the poles. So this will be our answer. Okay.
So D would be the answer.
Yeah. So
S.
yeah, this is also a simple question. Okay. Now yeah. Now the Bode plot comes. Now 14th question. What is the answer of the 14th question? Intuitive, and if you giving some, this answer is given, you have to tell me the reason also. Hello.
Yes, yes.
Do you have a basic idea on Bode plots, or should I discuss from the basics?
Sir, can you please discuss it from the basics?
Okay. See, Bode plots are generally describing a particular system, particular response of a particular system, frequency response of a particular system. Okay, it is a tool which it is a particular plot which describe in a particular glance what will be how the system behaves in frequency domain. Okay, now a particular system will have like each of s to be in this form only. What is the real form of each of s? Tell me, what is the real form of each of s? Hmm? What is general form? General form or transform? I am asking.
H of t?
H of s. I'm talking about h. What is the general? See. I think you are not getting my question. The general form is our particular system is 1 by s by omega z 1.
Ah,
into 1 plus s by omega
It's K.
z2 dot something, okay, and 1 by s plus omega p 1 1
Yes,
plus
yes.
s by omega p2, like this. Okay, this omega p omega z are the poles, omega z omega this one are the zeros.
Yes, sir.
Okay, now
Also, sir, A. In the
yeah,
start.
something dc gain is there, obviously. Okay, some dc gains are there. So if we do the Bode plot of this, okay, so for each and every, so Bode have two plots. Bode plots have two plots. First is Bode magnitude plots and second is Bode phase plot, and both are the important. Okay, but for the, like, generally we care about magnitude in a particular system. Generally we care about the gain of a particular system. That's why we generally draw the Bode magnitude plot. But Bode phase plot also tells many more things. Okay, so that's why those both the plots are important. But in this session we'll discuss about, like, we have more problems on Bode magnitude plot. Okay, I will discuss about that. Okay, and I'll also tell you the what is the Bode phase plot also. Now let's say I am taking a particular simple system. I'm taking a first simple system. Let's say I'm taking uh, h of s equal to 1 by s plus say 2. Okay, no. The most simplest system can be formed like this: 1 by s or s, right? So for a particular system, so this will be 20 log of h of s mod, and this will be omega in log scale, means log omega will be there. Okay, okay. Now a pole contributes a minus 20 dB per decay in Bode plot, and a 0 contributes a plus 20 dB per decay in Bode plot. So what will be the slope of this one? It will be minus 20 dB per decade. Decade means for multiple of tens. Why decade? Because this log base is 10, right? Okay, this is a non-linear. First of all, you have to remember this is a non-linear scale. So the thing is, like, what is the profit of this non-linear scale?
It is a common log, not a natural log. That's
Yeah, it's
why.
a common log. So that's why it's decade. So you can also form 20 dB per octave. Okay, so 10 octave equal to 0.3 decade. Okay, so this is a general formula to you. Generally we consider a decade scale only. Okay, but this is, we can also form the octave scale. In octave scale there will be eight divisions. In decade scale there will be 10 divisions. Okay, simple. So don't need of this. Okay, now see, this 1 by s pole will contribute minus 20 because this is a pole, right? It's a pole at s equal to 0. S equal to 0, there is a pole. So this will contribute a minus 20 dB per decade slope. This is minus 20 dB per decade. Okay, and 0 will similarly exactly opposite to this. 0 will cause a plus 20 dB per decade. Okay, 0 20 dB per decade. Okay, and this is also 20 log magnitude of h of s. This is omega. Okay, now
Yes.
I am taking another transform function. Let's say we am taking uh, a simple one only. Okay, so h of s will be 1 by s into s plus 1, let's say. Okay, and let's say I am taking here h of s equal to s by something, let's say s plus 2. See, this is s square. Okay, this is s square. Now what will be the Bode plot of this one? This is 20 log of this is log omega. Okay, I am not writing this, I'm not marking the x's. Okay, so this will be like, first it will have a minus starting slope of minus 20 dB per decay, because there is a the pole zero plot of this one is like this only, right? So first we have a pole. Okay, we are moving like this. First we have a starting slope of at s equal to 0, there is starting slope. Okay, minus 20 dB per decay. s equal to 1, at omega equal to 1, this omega equal to 1 is called as a corner frequency. Every frequency that where the slope changes, that frequencies are called as corner frequency. Okay,
Yes, sir.
so this is omega equal to 1. Okay, here another pole comes. So what I told, a pole contributes a minus 20 dB per decay slope. So here also, so previously it was minus 20 dB per decay. Again we are giving a minus 20 dB per decay slope. Now the slope will be
minus 40.
minus 40 dB per decay. Okay, now for this one. So initially we have a, how much initial, so what is the initial slope here? Can you tell me? What is it? Huh?
Plus
It is
40?
Plus 40.
Plus 40.
Yes, because once 10 gives plus 20.
Yes, sir.
So 20 will give plus 40.
Yes, sir.
And then a pole scheme, this is plus 40 dB per decay. Now a pole came at this corner frequency omega equal to 2, a pole came. So what will be the ultimate slope?
Minus 20?
No.
No,
See,
40 minus 20.
exactly. Previously
20.
40 dB per decay was there. Now this pole comes and this pole gives a minus 20 dB per decay slope. So ultimate slope will be 40 minus 20. That will be how much?
20.
20 dB per decay. You got right?
Yes, sir.
Now let's say I am giving this. Let's say I am giving you this. And I gave you this omega equal to 5. Now can you tell me what is the transfer function? And let's say this is A, whatever. So h of s, see, here there is no initial slope, right? Initially the response is flat.
Yes, sir.
Zero, slope zero.
There is A.
So this signifies that there is no poles and zero in the origin. In the origin, he said s equal to 0. There is neither pole nor zero, because initial response is flat. Okay.
Means this is 0 dB decay.
Yeah, 0 dB per decay. 0 dB per decay. Slope is 0 dB per decay.
Yes, sir.
Yeah, and this is minus 20 dB per decay. Yeah, I should mention the slope also.
1 by s plus 5.
1 by s plus 5. But there is a catch. There is a drawback
Catch.
here. We have to consider this A, because there is a DC gain, right?
Yeah.
Right. Okay. So you got the basic Bode plot, right?
Yeah.
Now I will discuss this. Okay. So there is so now so for this 14th question, can you tell me what is the ultimate slope of the 14th question now?
Minus 20 because we have 1 0 means plus 20 and we have 2 poles means minus 40.
Exactly. Very good. Ultimate slope will be minus 20. Because see, if you solve this, the what is the roots of this one? S equal to minus 4 plus minus root over 16 minus 20 by 2. That will be minus 2 plus minus this will be 2
2 iota.
J1.
Okay.
Sorry, J1 is.
2.
So what is the
Oh,
So it will be 2. So 2. 4
No, sir,
under
is
root.
getting correct.
I already divided.
Okay. I haven't seen that.
So my pole zero diagram will be like this. So at minus 2, this will be sigma j omega. Okay. So this is a S plane. This will be, let's say this is minus 2 and this is minus 1. So at minus equal to minus 1, we have a 0 and we have a pole here. We have two poles here. So for these two poles, we consider minus 40 dB per decay. Okay, and these two zeros will give a plus 20 dB per decay. So overall slope will be minus 40 plus 20 will be minus 20. Okay. Now we'll go for this. This is the good question. Okay. If you go for this will surely like these kind of questions are not even asked in the gate also, like this much of a level question. Okay. In gate, in from body plot there will be
But
simple.
it will be asked in end term. It will be there in the end term, like comprehension type.
Okay, maybe they're like, but this kind of solution will be much more easy. Like whatever told you now, I will go through the solution process of this one. You will at any step you will not find any difficulty. It will be very simple. Okay. Now see, for this circuit, so h of s will be something k into, okay, something k, because the initial slope is how much? 0 d per decade, right?
Yes, sir.
And some dc gains are there.
Yes, sir.
So
1 by s plus 2, s plus 5.
so see here, at omega equal to 2, we have a minus 20 dB per decay change. So you have to see mark my words. I am saying about change, slope change. While finding that Bode plot, while finding the transfer function from the Bode plot, you have to always notice what is the changes in the slope. That change will give you pole or zeros. Okay.
Yes, sir.
So that change will define corner frequency.
Exactly. Not that change will happen in the corner frequency itself, but that change, the slope change will define you how many zeros or how many poles are there in the corner frequency.
Okay.
At a particular corner frequency, there can be multiple poles and multiple zeros, right?
Yes, sir.
So that change will give you that what is the number of poles and zeros occurring at that particular corner frequency. Okay. Now see, at omega equal to 2, there is a minus 20 dB per decay. So can you tell me what is the there will be poles or zeros first of all?
Will be pole.
Yeah. So the poles form will be 1 plus s by 2, right?
Yes, sir.
I told you there is a general form. Okay. And we'll always form the transformation in the general form to avoid the like if you form in another form there can be a mistake. So in general form, generally there is a less chance of mistake. That's why I'm like keep on improvising this is, make it general form. Okay. Now at omega equal to 5, there is also a corner frequency. There is also slope is changing. Okay. Now what is the slope change?
Minus 20.
Yeah, previously it was minus 20. Now it was minus 40. So slope change is minus 40. So it will be 1 by s plus s by 5. Now at s equal to 50. Previously it was minus 40. At s equal to 50,
Increment of 40. So
Yeah.
40 increase.
40 increased. So there will be zero or poles.
2 poles.
Yeah, there
2
will be
zeros.
2 zeros, correct. At 2 zeros at what frequency?
Plus
1
40.
plus s by
1 plus s by
50.
50. This much.
To the power 2.
Yeah, 50 square. Yeah. Yeah.
Again, there is a decrement, so
Or minus
1
20
plus
dB per
s
decay.
by- yeah.
Right? So there will be a pole. At what frequency?
1 plus s by 200. 100. Yes, sir.
100.
100, right?
Yes, sir, 100.
Yes, sir. Yes, sir.
Finished, right?
No, sir. I think there will be 0, right?
Exactly, there will be a zero. Many guys actually I also used to do much more, like I have done a lot of mistakes in this kind of things. See, I'll tell you something. If the initial slope is zero, sorry, if the final slope is zero for a particular Bode plot, the number of poles and the number of zeros should be equal. Now see, here are 3 poles, only 2 zeros are there. So there must be one another 0. Okay. So at omega, see now this was minus 200 dB per decay. Sorry, I minus 220 dB per decay. Now here it became 0 dB per decade. So obviously at
Plus
omega equal
20.
to 200, there will be another 0. 1 plus
1 plus s by 200 the whole square.
exactly.
No.
No whole square.
No, not whole square, only
Not
one.
whole
Yes,
square.
no whole square. Okay.
So what is the note here? The note here is if the final slope of a particular Bode plot is 0 dB per decade, okay, then the number of poles and number of zeros should be what? Same. Let's say if the final slope of a particular Bode plot is minus 20 dB per decay, then we can say about the poles and zeros that the difference between the number of poles and number of zeros will be 1, and there will be one, like this one will be extra one pole. You are getting now?
Yes, sir.
Yes, sir.
If the final slope is 20 dB per decay plus 20 dB per decay, then the 1 0 is extra. 1 0 is more there as compared to number of poles. Okay, getting right?
Yeah.
Yes, sir.
So this is the transfer function. Okay. Now how can you say about this k? This k will be how much? This at this k, what is the frequency? 40, right? So
Yes, sir.
20 log of k will be 40 dB. You can get the value of k here. Okay, you can get the k value here. Okay, and if you get the k value for forming now, see these kind of things. These kind of, so k will be k you can find here, right? I'm not calculating it.
It's
Okay,
100.
yeah, k you can get by from this relation. You can get the value of k. Now how can you get the value of x here? That is the main thing. How can you get the value of x here?
Which x, sir?
This x.
Oh, we need to do some geometry, I think.
So what will be your process? This k value finding. So see, our main work is done. So if we find this k value, I think k values will be how much? It will be It will be how much? 10 to the power of
100.
2, right? K equal to yeah,
He is 100.
100 is 100. So now if we put the k value here, we already found out the what is the transfer function. So transfer function will be, so 100 into 1 plus s by 50 square, 1 plus s by 200 by 1 plus s by 2, 1 plus s by 5, 1 plus s by 100. Okay.
Yes, sir.
Yes.
So now to find the k value, okay, we have to do the Bode asymptotic plots. Okay, this is called first of all, this is called as Bode asymptotic plots. Okay, this whole plot is called as Bode asymptotic plots. Okay, and I talked about also poles and zeros contribution in a particular Bode magnitude plot, and so also in Bode phase plot. Okay, do you know how a pole contribute how much degree? A pole always
90.
yeah, minus 90, not 90. Okay, a pole contributes minus 90 degree, and zero contributes a plus 90 degree. Okay.
Okay, sir.
Okay, understood. You are taking reference as the x-axis.
Yeah, this is the omega axis. X axis is the my omega axis.
Yeah.
So how to found this value of x?
By making first, we have
See.
slope.
Now for a Bode asymptotic plot, like not taking any reference, you can find directly. I'm like telling, I will tell you a method. The thing is, now we have to find the value of x, and this value of x will be in the corner frequency of -5, right? Corner frequency of
Yes,
-5.
sir.
Now I will put all this. I will put the frequency I can put this s equal to at place of s equal to j omega, and that at the place of omega I can put the value of 5, and I can calculate the exact value that will give me the exact value. Okay, but in this situation I will do the asymptotic value. Okay, this asymptotic value will be whatever be the lower frequency while lower frequency occurs in the like lesser than this 5. Okay, that will not be considered, that part will be omitted. We can simply omit that part, and whatever be the higher frequency I will take the only frequency part. What does it mean? I will take this 100. Now see, if we put s equal to 50 here, is equal to 50 here. Sorry, is equal to 5 here, because my corner frequency is 5. I have to calculate the magnitude at frequency of 5, right? Now, if I put s equal to 5 here, omega equal to 5 here, now 5 by 50 is much more lesser than 1, right?
Yes, sir.
See,
Yeah.
similarly, this 5
1/10 part.
similarly, this 5 by 200 will be much more lesser than 1.
Yes, sir.
This part is also lesser than 1. So for these
We
parts
can
only,
ignore that.
I will take only one square. This is because this is only one will be left. I will simply omit this one. Okay. For this we don't know, till now we don't know. For this I can know that, I know that this will give me 1. Okay, this much clear.
Okay. Yeah.
Yes, sir.
Now if we put here s equal to 5, s equal to 5, okay, I will take only this part because this is greater than 1. Whatever be the greater one, I will take that one.
So 2.5.
Yeah, this will be 2.5. And for this, whatever, like it is same. Okay, you take this part,
3.5.
it doesn't matter.
One.
The one only.
So it will
Okay.
be 3.5 now.
No, 5 by 5 by
2.5
12.
plus 1.
No. I will take only the greater part. I will tell you now. Whatever be the greater part, I will take only that part and I am omitting the other part. That is the asymptotic calculation.
Okay,
40,
sir.
sir. 40.
Asymptotic means it's an approximated calculation. See,
Okay, sir, get it.
the thing is, what is the body? This is not a body exact plot. Okay, this is the body asymptotic plot. The body exact plot will be look like this only. See, if I take a simple RC low pass filter, the transfer function of h of s will be 1 by SRC plus 1, right? Or R by SRC plus 1, whatever. Right?
Yes,
Hello?
sir.
So if you plot the transfer function of this, it will be like this only, right? Minus 20 per decay. Initially there is no poles and zeros. After some time, at 1 by RC, there is a pole. Okay, and there will be minus 20 per decay slope. This is the Bode asymptotic plot. Bode exact plot will be look like this. Okay.
Okay, sir.
This is not, there is no sharp edge like this. Okay, so that's why.
Okay, sir.
So this is the approximated analysis. In a practical circuit, this may look like
Yes,
this
sir.
only. This
We
may
have
look
done it in low
this-
pass filter and high pass filter. These
Yeah.
graphs.
yeah. In a Bode exact circuit, this will look like this. This is the Bode exact plot. This one is Bode exact plot. But whatever I done in the question, that is Bode asymptotic plot. In the questions also, it will be given Bode asymptotic plots. Okay. Now this will be 40, right? Okay.
Yeah, 40, 40.
So 20 log x is 40. Okay. No, not 40.
It will be 40.
So x equal to 40. So this is directly x, right? This is already considered. Why I'm taking this? I don't have to consider this 40 again. This will already give you the value. Am I doing something wrong here?
Sir, can we do that? Find that x value by using tan theta is equals to perpendicular upon base.
No. That will not. That is not a linear scale. It is not a linear scale. This is a log
But
scale, right?
for a little part.
Huh?
But for a little part that there.
We can't. How can I calculate the entire part also? Like this is not a linear scale. for the tan theta we have to be given the phase plot. From the phase plot that will give a angle. From that we can calculate the x value. But the thing is the phase plot is not given, right? How can I, like, this is see this is not a linear scale. This is not a linear scale. Okay, that's why we can't do that.
Asymptotic function.
Yeah.
Okay, sir. Get
No,
it.
this is not a case of asymptotic function. This is the thing is this is also log scale. This is also log scale. Okay.
Okay, sir. Okay, sir. Get it.
So that will give me 40, right? Okay. So what is the x value? 20 log of 40. That will give me the x value. Okay, that will be in dB. This is radian. So 20 log to 40 will give me the dB value. So x will be in dBs. So see, x is considered in dBs. This 40 is radian. Okay, you should also like careful about this. So can you do like this calculation? 20 log. What is the value of 20 log 40?
Yes, sir, we can do, sir.
Yeah, do it and tell me the answer. Just put it in the calculator and tell me.
1.6 into 20.
Sir, one simple calculation. Log 40 we can write log 4
32.
into 10, and then we can use that property of multiplication log 4 plus log 10.
Yeah, then also we need to know the what is the log 4. Just do it in the list.
So log 4
Sir,
will
2
be
to the power 2. 2
yes,
into
2 into log 2.
0.3.
What is the log 2 value then?
Sir,
So
I'm
log 2 we have to
30.
remember. No, sir,
I
there
think-
is a scientific calculator in the end. No need to.
Yeah. That will be scientific calculator. Okay. Okay. So that's all the thing. Okay. So do you have any doubt in this question? Anyone?
No, sir, but a small doubt. Can you scroll up?
Okay. Just give me one thing.
No, sir. In this screen only 100 into 1 plus s by 50 whole square into 1 plus s by 200. Why it is not whole square? Why it is only the single term?
Because what is the change in slope?
Sir, the change in slope is minus 20.
Change in
Okay,
slope.
okay.
Change in slope
Is
is
20.
change in
At
slope is minus
200,
20.
like what is the slope
See,
at 200?
previously it was 20 d per say. I should clear it.
Yeah, minus 20. So, yes.
So previously it was plus 20 d per decay. Now it is getting 0. So 0 minus plus 20 means minus 20 d per decay. Right?
Yeah.
So for minus 20 d per decay, a pole should come or a 0 should come. Sorry. See, why this is what I'm doing? See, it is a negative slope, right? This is minus 20 d per decay is given.
Sir,
So
positive 20.
0 minus of 20 minus 20. This will be plus 20 d per decay. This is a negative slope, right?
Yeah. This is a negative slope, and the change is positive.
Yeah, change is positive, so obviously 0 should come.
Yeah.
So 0 is coming.
Okay, got it.
Any other doubt?
No, sir.
Okay. Then you can leave the session.
Okay, thank you, sir.
Yeah.
Thank you, sir.
It was a wonderful session. Learned a lot from you.
Okay. Thank you. You guys are also so supportive.
Thank you, sir.
Okay. Bye all.